Hello, I'm Madeline Navarro, and I'm presenting our work on extending Mixup for augmenting data in different directions. So data augmentation is a technique where you can generate synthetic samples for an existing data set to alter data-driven model behavior. So for example, say that I want to learn this function in gray from these observations in red. Without enough information, we might have the wrong prediction outside of our observations, maybe because we don't have enough observations to understand what kind of behavior we would have outside of outside of our training data. But say that I add synthetic samples in between every pair of adjacent observations, and then when we try to when we try to learn the underlying model, we get a much more accurate prediction. So data augmentation can help you mitigate overfitting by adding more samples to your training data if you have appropriate prior information. And Mixup is a very popular and efficient technique for data augmentation, where you take convex combinations of existing labeled samples and you use those as new labeled samples in your data set. So for example, if I have these two images, one of a tree and then one of a car, then I can take their average and say that this is a new labeled image that is halfway between a tree and a car. And so because Mixup is very successful, both empirically and theoretically, we want to kind of extend its usefulness in different directions. And this is what I'll be talking about today. So we have three directions in particular that we're extending Mixup, or in which we're extending Mixup. So first, we want to look beyond the case where we're taking these convex combinations of just pairs of samples. And then we'll look beyond Euclidean domains to look at Mixup of graphs. And then finally, Mixup is primarily applied, and data augmentation in general is primarily applied for improving model performance in terms of accuracy, but we want to see if we can apply the advantages of Mixup for promoting other kinds of desirable model behavior. So first we'll look at going beyond pairwise linear Mixup. In expectation, what Mixup is doing is it's promoting linearly varying uncertainty in between pairs of classes. But the way that we're doing it is just by taking two samples at a time. So you might be missing some valuable contextual information about the remaining samples in the data set. So for example, so the thing is, the concept of linear Mixup is that the further away you are from a particular class, the more uncertain you should be. So what that also means is that if we have a dense cluster of samples for a particular class, we should probably be more confident in that region. And then if samples are more spread out for a particular class, we should be more confident for a wider region. But linear pairwise Mixup in expectation will encourage the same linearly varying uncertainty because it's only looking at two samples at a time. So we want to take advantage of the similarities among all of the samples in the data set so that we're not missing out on this kind of valuable information. So we want to look for a technique that considers the relationship among all of the samples in the data set. So we're inspired by clustering techniques, and in particular hierarchical clustering, which assigns cluster labels to samples based on how similar they are to each other. And so for hierarchical clustering, we get this dendrogram, which gives a kind of ranking of how we should group samples together based on how similar they are to each other. And what we can do instead is we can consider this convex relaxation of hierarchical clustering called convex clustering, which gives you the same critical fusion points for groups of samples, but then we also have this continuous function in between these fusion points. And the rate of change of this continuous function tells you how similar different clusters of samples are to each other. So more formally, convex clustering solves this optimization problem, which returns these U-hats, which are cluster centroids assigned to each sample. So if two samples have the same value for their cluster centroids, then we say that they're part of the same cluster. And so convex clustering is trying to minimize between these two terms. One is a fidelity term and one is a fusion term, where the fidelity term is trying to fit each cluster centroid to its associated sample. And then the fusion term is trying to encourage cohesion among the different clusters. And then we trade off between the two with this fusion parameter lambda. So when lambda is 0, then we just have the fidelity term, and so all of the cluster centroids are just the original data samples. So we have all singleton clusters consisting of each of the distinct data samples. And then as lambda increases, then we start to encourage more fusion of the samples. And then once lambda approaches 1, then all of the samples are assigned to the same cluster. And we can also look at this visually. So this plot is this dendrogram is the the cluster centroid paths from convex clustering for a labeled data set. And so each of these branches corresponds to one of the cluster centroids as you vary lambda. So the x-axis is the one-dimensional PCA embeddings of the cluster centroids that we obtain from convex clustering. And the y-axis is the fusion parameter lambda. So when lambda is 0, we just retain all of the original samples. And then as lambda increases, then the clusters begin to coalesce. And then when lambda is 1, then we have just one cluster of all of the samples. And so that the way that we will apply these, the way that we'll apply this dendrogram for mix-up, since we're doing this for classification, we have each of the samples are assigned a class label. So for mix-up for classification, what we do is we take all of the cluster centroid paths corresponding to each class, and we kind of collapse them into one branch per class, which is just averaging the paths for each class. And then to obtain a sample mixture, we'll choose a level of fusion by choosing a value of lambda. And then we'll look at the cluster centroid at that particular value of lambda. And the cluster centroid at this point will be a mixture of the original data samples, like a convex combination of the original data samples that is varying according to how similar all of the samples are to each other. So this gives kind of a more informative way of mixing up data samples that takes into account the context of the entire data set. So it's more informative than pairwise linear mix-up. Okay, and so I'll show an application of this in the next section, which is our extension of mix-up for non-Euclidean data. So mix-up for images is very straightforward and very popular because it's Euclidean data and it's all in the same domain. But it's not as obvious how we would perform mix-up for graph data. Even if you have two graphs that are on the same node set, it's not obvious how we would say what should halfway between the star graph and this grid graph be. So we propose graph mix-up for augmenting data, which is a 3-step procedure to obtain mixtures of graph data, or we'll obtain graphs that correspond to mixtures of the existing graphs in a labeled data set. So the first step is that we'll project all of the graphs in our labeled data set to a continuous embedding space. This is a really popular approach for mix-up of non-Euclidean data, and it works very well as long as your latent space is preserves semantically relevant information. And then once we have these continuous embeddings, then we can perform mix-up in whatever way you choose. You can do linear mix-up or the convex clustering mix-up that I just proposed. And then finally, since we want to perform classification in the original domain, we need a way to invert the embedding process so that we can sample new labeled graphs that correspond to mixtures of existing samples. So our choice of the continuous latent space should be able to be invertible, and ideally it would be a stochastic inversion so that we can obtain many views of the same mixture. So for our latent space, we'll consider limit objects of graphs. So limits of discrete objects kind of allow us to treat discrete objects like they're continuous. So if we consider this as a convergent sequence of graphs, if we have a convergent sequence of graphs, then as the number of nodes grows to infinity, the sequence will converge to a graphon, which is a function on the unit square that whose range you can think of as edge probabilities. And so because this graphon is associated with a convergent sequence of graphs, then it describes a family of graphs with a similar structure. And graphon estimation is a very popular task, or it's very common, where you take a single graph and you try to estimate the graphon that describes the family to which your graph belongs. And there are very efficient ways to do this, and there are some more complicated but more accurate ways to do this. And so we have a way to take a set of graphs and convert them to graphons, which are these nice Euclidean objects that lie in the same domain. So for our continuous latent space, we'll use the space of graphons, which is a superset of the space of graphs, which means that we're not really losing topological information, or we're hopefully preserving the important structural information. So once we have these continuous embeddings, where we've estimated a graphon for every graph in the data set, then we can perform mix-up using linear mix-up or convex clustering mix-up. And then finally, we need to be able to convert from some continuous graphon object back into the space of graphs. So a graphon is not only a limit object of a sequence of graphs, but the graphon can also serve as a random graph model. Okay, so the graphon can also serve as a random graph model where we can sample any number of new graphs of any size we want from the same graphon. So we can generate many graphs that have similar structure from the same mixture so that the model that we're training kind of understands what is being mixed, which is structural information. Okay, so then that's our third step of this process where we can invert from the latent space, which is the space of graphons, to the space of graphs where we can just generate any number of new graphs for a particular mixture. Okay, so in practice, we apply this to some graph classification data sets where we're comparing the original data sets, which is the top row, with the data sets plus augmented data using Mixup. So we compare a linear pairwise mix-up where we estimate a graphon per class, and then we do pairwise mix-up across classes. And then we also compare with convex clustering mix-up using the method I just described. And then we also wanted to look at if we use a different function for label mix-up versus data mix-up, because you might want the mixtures of labels to have a faster or slower rate than the features, which are the graphs in this case. And so what we observe is that Mixup using the graphon as a latent space is able to improve classification. So the use of the graphon as a latent space is preserving the semantically relevant information that we'd like, or at least empirically, we're showing this is the case. And then also the convex clustering Mixup outperforms the linear Mixup for all of these data sets because it is more informative, and it performs especially well for multi-class data. Because it's taking into account it's rather than only considering pairs of classes at a time, we can consider mixtures including more than 2 classes. And then also we see that using a different function for label mix-up can be informative, and it depends on if you want to encourage more certainty more quickly or more slowly. Okay, so this is an example of convex cluster mix-up and then mix-up for non-Euclidean data. And finally, we'll look at our work for using Mixup to improve model performance, not in terms of its accuracy, but in terms of if we can encourage fair model behavior. So it's well documented that machine learning models can inherit biases in real-world data. And even if the model is agnostic to sensitive information that we don't want the model to use. So we need ways to be able to remove biases from data so that we can obtain models that are fair. Because we can't just drop kind of sensitive features because they might be kind of correlated with other features in the data. So we need a way to kind of debias data so that we can obtain fair models. And when I say fairness, I mean we're considering group fairness where we have samples that belong to different groups, and we want the models that we obtain to have treat the different groups equitably, regardless of the values of the sensitive attribute. So probably the most popular definition of group fairness is demographic parity, where we want the distribution of the model's predictions to be independent of the sensitive attribute. In practice, we compute the empirical gap in demographic parity. And when this empirical gap is 0, we say that demographic parity is achieved. Okay, so then we want to, now what we want to consider is, can we use the abilities of Mixup for classification accuracy to improve model fairness according to groups. So let's say that we are considering data that belongs to one of 2 classes, but also one of 2 different groups. So the colors correspond to the different classes, and then the shapes of the markers correspond to different groups. The larger, lighter circles are the true distribution, and then the markers are our training observations. And yes, the different shapes are the different groups. So bias in data can occur from different kinds of, different situations. For example, you could have imbalanced representations of different groups, or you could have shifts in distribution across groups. So for example, if I were to use an SVM model to classify this data in this example, we would consider this unfair according to demographic parity because the ratio of predictions that are class 0 to class 1 for group 1 is much smaller than the ratio for group 0. So we want We might have to trade off accuracy for this, but we would want the model to have balanced treatment for every group. So we'll propose fair subgroup mix-up, where we'll take two subgroups, meaning a particular class and group, and then we'll take a pair of subgroups and then we'll perform linear mix-up in a way to encourage the model to be more fair. So if we mix up with the same class and across groups, then this encourages the model to be invariant to treat the groups the same for each class. So we'll promote model invariance across groups, which is exactly the definition of demographic parity. But then if we take the underrepresented group and we perform mix-up across classes and in the same group, then this can help because with data augmentation, of course, you can kind of address imbalanced data, and you could do this with bootstrapping. But because we're doing mix-up, we're also encouraging the model to kind of pay more attention to the underrepresented group, so that the model kind of can even improve accuracy as well as fairness, because it's learning data from each group individually, or it's encouraging more equitable treatment across groups. Okay, so we can show this, So fair subgroup mix-up can address these two types of biases, like imbalanced data, and then also shifts in distribution. So then we'll look at this for some synthetic cases to demonstrate these, and then we'll look at a real-world case with real-world data. So first, let's look at the case with unbalanced groups, where the darker markers are training observations, and then the lighter markers are the samples that we add using fair subgroup mix-up. So in this case, we have unbalanced groups because we have far more of these crosses than we do the circles. And so we add samples for the underrepresented group and then across classes, which will encourage the model to be more certain about the decision boundary that it assigns to the underrepresented group. And so we compare our model to data augmentation and bias mitigation baselines for random forest and for a multi-layer perceptron. And what we see is that for random forest, we can improve both fairness and accuracy. And then for the multi-layer perceptron, we can improve the fairness above the baselines without sacrificing accuracy. Okay, and then we can look at the case of unbalanced classes, where one class is underrepresented, but only for a particular group. So the model will probably be treating the groups fairly for the overrepresented class in red, but then for the underrepresented class in blue, it might be ignoring the presence of the underrepresented subgroup of blue crosses. So we add samples across groups, but within the underrepresented class. And we're encouraging demographic parity here because we're trying to encourage the model to treat both groups for that particular underrepresented class to be the same. Okay, so we compare with the same baselines, and then for a random forest, again, we see that we're improving both fairness and accuracy. And then for the multi-layer perceptron, we can improve classification while being competitive in terms of fairness. And then lastly, we'll look at a real-world data set of classification of law school admission. So the samples in this data set are law students, and we want to predict whether or not they'll pass the bar. And we have different demographic information, and we want to make sure that we want to encourage our model not to make its decisions dependent on race. And so what we have is that with our method, we're able to improve the fairness of the model without too much of a sacrifice in accuracy. And this is a very nice result because it's really hard to improve fairness of models without sacrificing some accuracy, because usually these sensitive attributes in the real world data are very correlated with the predictions that we want to make. So we're able to improve the fairness and maintain robust accuracy for real world data. Okay, well, in this talk, then I've shown you the 3 extensions of Mixup that we've done. We looked beyond pairwise Mixup to use this more informative convex clustering Mixup. We looked at Mixup for non-Euclidean data with graphs using graph limits. And then we've shown that you can use Mixup for improving model fairness as well. In the future, we want to formalize why convex clustering is more informative for Mixup. And we want to use the kind of well-established theory of graph limits to say what is happening when we're adding these new samples with these new graphs that correspond to mixtures of existing graphs. And then we want to do more interesting scenarios for Mixup for fairness, like using convex clustering or doing individual fairness instead, or having maybe more than one group attribute or sensitive attribute.